Welcome to AP Chemistry at Honega High School. I'm BBrown, and in this movie, we'll be looking at help getting ready for the Chapter 20 AP test, which deals with electrochemistry. First off, some common errors and misconceptions I often see. Some things about sig figs, cathodic protection, and so on. So these are things you need to watch out for in preparing for this test. First off, units and sig figs. Sig figs aren't as big of a deal. It's just more of what we've been doing, but some things related to units. For the equation, I equals Q over T. Remember, Q in this case doesn't mean heat. It means number of coulombs. T would be a time in seconds, and I stands for the number of amps. So remember, the unit of amps is going to be a capital italics A, and your Q is really coulombs, and remember the T is going to be seconds. Those are important when using this equation. So remember that equation's on the AP Cons sheet, but you got to know what the different parts and what their units are and look like. Second is the Gibbs to cell potential relationship under standard state conditions, because that's what the naught means here. Remember, we could erase the naught and we'd still be talking about all the same stuff. But remember, that is what that little naught sign, this circle right here, means. We are at standard state conditions, which would be standard conditions. Remember, that is 1 molar for concentrations, 1 atm for pressures. Now, in that equation, one of the things you need to remember is when you look up Faraday's constant on the AP constant sheet, you'll see 96,500. That's not the form of that we're using here. We need the 96.5 kilojoules per volt mole, because remember, cell potential E naught is going to be in volts, and we need to end up with a kilojoule per mole amount for delta G. Remember, the N stands for moles of electron transferred, and F is going to be our 96.5 kilojoules per volt mole. N, remember, is, and I mentioned this a second ago, from the balanced redox reaction. It's not the half reactions. You have to look at the balanced transfer between the two half reactions. That's what your N is going to stand for. Remember, delta G is usually in units of kilojoules per mole. But depending on what you're doing, like in this case, if you're multiplying by moles for N, and you've got volts for your cell potential, you're going to be left with kilojoules here, and that's perfectly fine. It's not really a big issue with this one, but one thing I want to mention related to this symbol right here. Remember, it has a lot of names. They all mean the same thing. The cell potential, EMF, which stands for electromotive force, and E naught. All of those things are referring to the exact same thing. So E is cell potential, and it's EMF, all the same thing. And then finally, since we do deal at times in this unit with K, remember K has no units. 2, cathodic protection. It's one of those things that, we didn't spend as much time, and it's really what section 28 gets into, is different applications of electrochemistry in everyday life. So you should take the time to make sure you understand, batteries and so forth. But one of the major ones is really the corrosion reaction. And we looked at that in depth in this section. You really should understand cathodic protection, because corrosion costs us billions of dollars every year, so it makes sense that it's important to understand this application of redox and how to prevent corrosion in the form of cathodic protection, like the magnesium anode that gets connected by a copper wire, an insulated copper wire, to our underground metal pipe here, which forces the underground pipe to become a cathode rather than an anode. Remember, anode oxidation happens at the anode, and ox is a memory aid with that. Well, if we allow the metal pipe to be an anode, it's going to rust, it's going to oxidize. But if we can hook a more reactive metal up to it, then the magnesium here, which is much more reactive, is going and more likely to oxidize than the metal pipe is. That's what's going to be oxidized, is the magnesium. So if it is more likely to be oxidized, more negative reduction potential, then it will force the magnesium to become the anode, which is where oxidation happens, and it will force the water pipe to become a cathode, which is where reduction happens. Remember, oxidation of a metal pipe means you need it to be the anode. So for forcing it to be a cathode, it's going to protect it from oxidation. Same thing happens with a galvanized nail. you should be aware of these things in this section because they're often overlooked. Balancing redox reactions in a basic solution. Remember, the way we looked at this was carefully, and that's important. Balance the reaction like normal, so you follow all of our acid solution balancing rules. And then when you're done, you have your final answer. Add enough OH to each side to convert the H pluses that will be there to waters. And then don't forget to finally cancel that on each side. So first, we have to get a balanced redox reactions through very careful application of our balancing rules. Check. Well, I see 8 H pluses here, so that means I need to add 8 OH minuses to each side. Check. And then that's going to convert these H pluses into waters. And then finally, I need to cancel these 8 with those 4 to leave you with 4. Check. So it's not hard, but be careful with it. And remember, you need to write this out and physically do it. Don't just try and do it in your head. You can make simple mistakes that way. Same would be with balancing the overall reaction. Now, that brings us to balancing the half reactions. One of the critical steps in balancing the overall reaction is balancing half reactions. And common mistakes are made in the overall balancing by screwing up the half reactions. And if I ask you to balance the half reactions themselves, or I'm asking you about what's being oxidized or reduced, you need to take the time to follow these steps. Take the time to write the half reaction and then follow the above steps to balance that half reaction. Do it carefully, write it, write it, write it. Don't just look at it and think you know where the electrons are going to go and what's happening, how it's going to balance. Physically write it down. And remember, once you've got first 3 steps done, you add the difference in charge between the two sides to the more positive side. That's how you decide how many electrons you add and where. And remember, write it out, do it. Don't do it in your head. Next thing, oxidizing and reducing agents. Remember the substance that is reduced, and remember, you are reduced when you gain electrons, or you're reduced when your oxidation number decreases. You can look at that from any point of view. They both are the same thing. That, whatever is reduced, that is your oxidizing agent. And then your reducing agent would be the exact opposite. What is oxidized? What is lose electrons? What has an oxidation number that increases? That's oxidized. That would be your reducing agent. Remember, the oxidizing agent is what causes the oxidation, which is what is reduced. Be careful of that opposite situation. Next, electrolytic stoichiometry. I think people they think too much is going on here, so they just guess and they don't take the time to really do it. It's not bad. Stoichiometry is one of the keys to chemistry. You use it in so many different applications. All stoichiometry is the same thing. Remember first, if it's stoichiometry, you have to have a balanced equation because we're converting from one thing to another in stoichiometry. In the case of electrolytic stoichiometry, it involves a conversion between moles of electrons and moles of a metal. So you're going back and forth between those two things. Well, you need a reaction because you need a mole ratio in order to do a conversion between one thing and another. The mole ratio that we look at comes from the balanced equation. That's not the overall redox reaction. It's the balanced reaction of the half reaction described. So if it's talking about, molten aluminum or aluminum chloride becoming aluminum metal, that's Al3 plus, and it's becoming Al. I've got to add 3 electrons to the left. So first establish the reaction that's talking about in the problem. The electrons may be on the left or the right. In the end, what's really important is the numbers involved. That's where we get our mole ratio. Now remember, in all stoichiometry, we're always going from one thing to another. That actually comes in the middle of our problem. So think of it as 3 steps, and the stoichiometry part is really that middle step. It's just always there. And really, you need to decide whether you have to do something before and something after that. So our first and third steps will involve getting to moles if we're not in moles, and getting out of moles if we don't want to go to moles. Well, in the case of electrolytic stoichiometry, you're always going to do those first and third things. Now, what's going to take place in those first and third things? Well, one's going to be a molar mass conversion because this equation deals with electrons and it deals with our metal. We could be converting from electrons to the metal or the metal to electrons. And remember that deals in our mole ratio with moles between the two things. So once we get this, or if we need this, that's going to involve our molar mass. So in the case of the aluminum reaction here, that would be, how many grams of aluminum equal 1 mole of aluminum. And that's what you get off your periodic table. So remember, if our mole ratio involves moles of electrons and moles of a metal, we've got to get to moles of our metal or get out of moles of our metal using molar mass. Now the second thing here is our mole ratio deals with moles of electrons. So how do we handle this part of this in the first and third step? Well, we're either going to be getting to it using Faraday's constant, which is what's right here. So if we know the coulombs, we could use this coulomb to electron equality as a ratio to get 2 moles of electrons. Or if we're at the end of the problem and the moles of electrons come at the end, we would use this same relationship to get to coulombs. And that really leaves, well, how do I get to coulombs or how do I get out of coulombs? Well, that last thing is the current equation. I equals the number of coulombs over the time in seconds. Now remember on the equation sheet, this is going to look I equals Q over T. And what you really need to remember here is if we want to find coulombs so that we can change coulombs to electrons and then electrons to moles of our metal and then moles of our metal to grams of our metal, we need to do this at the beginning. We need to take our amps times our time in seconds, and that would give us our coulombs that we could plug and start our stoichiometry with. Or if we're trying to find the time, the seconds, we would do the stoichiometry part first. We take our mass and use molar mass to convert to moles. Then I can convert from moles of, let me walk through that with arrows again. Then what we could do is we could take our mass of our metal and convert it to moles of our metal. And then we go from moles of our metal to moles of electrons. And then moles of electrons to coulombs. And then at the end, we could use this here, take our coulombs and divide by the amps to get our time in seconds. So realistically, it's the same thing, but in reverse. If you're going from the mass of the metal plated to how long that took, or if you know how long it took at a certain amperage to figure out how much metal mass could be plated out. You're just going to do the same thing but in reverse. But it's still going to have in the middle that basic stoichiometry step where you're going from moles of one thing to moles of another, and then you're just going to do things at the beginning and the end. Now, here's what a typical problem would look like. What mass of aluminum is produced if 10 amps is applied for 1 hour to an electrolytic cell containing molten aluminum chloride? Well, if we've got molten aluminum chloride, we've got Al3 plus, which we need to add electrons to reduce it to aluminum metal. Now, it's really asking how much of this metal? Well, in order to do this, we have to basically get to electrons. Well, that's going to start with our amps and our time. But remember, coulombs per second. So we need to be in seconds instead of hours. So 1 hour is 3,600 seconds. We can multiply that to get our number of seconds. Multiply that by our amps, which is coulombs per second. Seconds would cancel and we have our coulombs, which would be 3.60 times 10 to the fourth here. Then we could use our Faraday's relationship, which is on the AP constant sheet. Then we could use our mole ratio, which comes from our balanced equation here. And then we'd use molar mass, and we would end up producing or predicting how much metal we produced in the course of this reaction. So that's electrolytic stoichiometry. Remember, if they give us the mass, we're just going to start with this, and then everything is going to get flipped. So we're going to go from the mass to moles, the moles of aluminum to moles of electron, the moles of electrons to coulombs, and then we would use this and this to find how many seconds. So it would end up being the number of coulombs divided by the amps would equal our time in seconds. And last thing, and this is something that you haven't spent enough time worrying about since the beginning of the year. Remember we talked about how you got to know polyatomic ions. Pops up in a number of different chapters. This is one of them. If they're talking about a redox reaction between, nitrate and nitrite, if you don't know what those things are, then you can't end up getting the right balanced half reaction. So it's kind of hidden in this chapter, but it is important that you understand the formulas of polyatomic ions because it may be very relevant in the course of a question. So those are some of the things that deal with some of the important misconceptions. Another thing I wanted to quickly look at was just some math and concept ideas related to things in the chapter 20 chapter. First off here, just some things about electrolysis, electrolytic cells, um, Remember, you should understand how an electrolytic cell is different from a voltaic cell. And remember, that deals with spontaneity. And remember, that deals with if you're going to need a voltmeter or a voltage source. If you got a voltmeter, it's a spontaneous reaction. You're talking about a voltaic cell, not an electrolytic cell. If you've got a voltage source, that means you're pushing electrons against the grain. That means you're forcing a non-spontaneous reaction to happen. And remember, the charge of the electrode is different. What happens at the anode is still oxidation. What happens at the cathode is still reduction. Those things still apply, but the charges will be different between the two. It's only anode is negative and cathode is positive in a voltaic cell. Those charges would be reduced for an electrolytic cell. And also, you should basically be able to do two things with electrolytic stoichiometry. That's what we just looked at. Find the mass of a metal plated and find the time it takes to plate a certain mass of a metal. Those are the two things you do with electrolytic stoichiometry. Now, other related ideas in the chapter. Oops, I actually started with the very end. So we're going to walk through these backwards. So those are some concepts. These are some math ideas that you should be aware of in the course of this chapter. Remember, if you're calculating delta G from E naught, then you're using the Gibbs equation. This is on the AP constant sheet. And remember, if it's asking you to calculate delta G, I should say delta G naught from E naught. If it's asking you to calculate delta G from E, you just erase these. And if you knew what the E is, and you multiply the F and the N, remember that's Faraday's constant. We talked about this earlier, got to be in very specific units, and N is the electrons transferred. Next, if you want to calculate K from E naught, this is the equation you use. Once again, this is on the AP constant sheet. You just got to remember N is your electron transferred, and you need to be able to get rid of a logarithm. Nernst equation. If you're calculating non-standard cell potentials, E instead of E naught. And remember, that's going to be when you're not at 1 molar concentration, not at 1 atm pressure. So if they're giving you pressures and concentrations, you're going to be using the Nernst equation. You either are given E naught or you have to find it using cell potentials. And then you're going to subtract from that how much that changes based upon that equation. And remember the Q we're looking at here, that is the equilibrium expression. So write your equilibrium expression and plug in your non-equilibrium things. That's why we call it in the right places. That's why we call it a Q instead of a K. Backing up further, other math problems that you need to understand here. Calculating the E naught of the cell, that's cell potential ENF of a voltaic cell, and electrolytic cells. Remember to do it from either one. Use this more general equation. The E naught of the reduction potential of what's being reduced minus the reduction potential from what's being oxidized. That works for any situation. And remember, know the meaning of the positive and negative values for E naught. When it's negative, it's non-spontaneous. When it's positive, it's spontaneous. Opposite of Gibbs. Standard reduction potential table. Be able to use it to tell what is reduced and what is oxidized between two substances. Remember, the more positive reduction potential is the more likely to be reduced. The less positive is the more likely to be oxidized. And also be able to use the relative strengths of oxidizing and reducing agents. Remember, the more positive, the more likely it is to be reduced. That's the stronger it is as an oxidizing agent, and vice versa. Voltaic and galvanic cells. What makes an electrochemical cell a voltaic cell? Remember, if it's spontaneous, it's going to be a voltaic cell. Know the parts of the voltaic cell. Know what's going on at the anode and the cathode. Be able to figure out where it is based upon electron flow, what the charge is. Voltaic cell, anode would be negative, cathode would be positive. And does oxidation or reduction occur there? Well, that would be anox, oxidation at the anode, red cat, reduction at the cathode. And remember, to find what's the anode and cathode, that would be fat cat. Electrons flow from the anode to the cathode. Also, deal and understand that idea of electron movement, which I just reviewed. Also know what's happening with ion movement. Remember, the reason we called it the cathode is because cations are moving at it, and the anode anions are moving at it. Function of the salt bridge, remember that is to maintain charge neutrality. And what happens to the mass of active metal anodes and cathodes? Well, at the anode, you are actually taking an oxidation reaction. So that means a metal is becoming an ion. That's oxidation. So on an active electrode, then that would mean at the anode it's getting lighter, and at the cathode, if it's active, it's getting heavier because you'd be plating an ion on top of the metal. Remember, in an inert electrode, that's just a site of electron movement. The mass of the electron isn't actually changing at all over time. Oxidation numbers, first thing we looked at. So in our reverse direction here, this is the first thing from the chapter. Make sure you can assign oxidation numbers. Key idea is, remember, oxygen is generally -2. Hydrogen with a nonmetal will be a +1. With metals will be a +1. And the big idea from there is the total of the oxidation numbers equal the charge. Knowing those few things, you can figure out most oxidation numbers. And remember, it is possible for them to be um, non-whole numbers. They can be halves and thirds and so forth. Redox reactions, be able to identify if it's redox. Remember, a big clue is if it has a elemental substance on one side or the other, because it's going to be changing. So it's going to be going from 0 to some charge. Identify half reactions as oxidation or reduction by either looking at it from an oxidation point of view or where the electrons are. Identify what species or element is oxidized or reduced. So remember, what stuff on the left is being oxidized, what stuff on the left is being reduced. Also be able to identify the oxidizing agent or the reducing agent. Remember, what is reduced is the oxidizing agent because it causes the oxidation. And what is oxidized is the reducing agent because it causes the reduction. And remember to be able to balance not only your half reactions, but be able to balance electron transfers once you have two balanced half reactions and get the overall balanced redox reaction in both acidics and basic environments. And that's the stuff you should know from chapter 20, both math and concept wise, as well as some of the key misconceptions. Good luck on the test.